Hey, Zoomers. Cool. Hello, everyone. Yang Song, can you hear me? Hi.
Yeah.
Cool. SangHyun, thank you for joining us. Today's lecture is the first lunchtime young lecture series. Today is covering algorithmic projects, and we are happy to have Yang Song and SangHyun Suh joining us today. Let me unshare my screen so you can see everybody's face. Hi, this is everybody. And we also have few people are joining soon. Yeah. So we are going to have Yang to start, and there will be 15 minutes each, two presentations, and then we will have discussion sessions afterwards. Cool. Welcome, Yang.
Yeah, let me share my screen. Can you see the screen?
Yes.
Okay. Okay, so hi everyone, and thank you for inviting me to join the Young Lecture session in the AAVS School Social Algorithms 2022. So during today's lecture, I would like to share my PhD preliminary research works in the University of Liverpool. So the title of my presentation is called Design to Fabrication, an on-site AR immersive design to robotic fabrication framework for memory structures. So first, let me have a brief introduction about myself. My name is SangHyun Suh, and I got the master's degree of architecture from the Bartlett UCL. And I started to do the cross-discipline research related to architecture design and augmented reality technology. So for now, I'm a practice-based PhD student from the research group CAVA, the Center of Architecture and Visual Arts, University of Liverpool. And I continue my previous research direction and try to add the robotic fabrication technology into the AR-assisted workflow to explore the interaction between human, robots, data, and their mutual relationships through the immersive design to fabrication process. So this research project is supervised by Professor Richard, who is the chair in architecture and visual arts, and he is interested in digital database and also immersive media like VR and AR technology. And this research is also supervised by Sirius, who is the director of architecture school. And his research includes about the parametric design, generative design, VR, AR, robotic, and digital fabrication. So this is my research timeline, which is divided into 5 main parts, including the literature review, the research gap and aim, framework methods, experiments and findings, and the final thesis writing. So at the beginning of my research, I start to do the literature review and try to find the current research gaps about the AR technology applications in architectural design methods and also the robotic applications in the digital fabrication. Try to find out the limitations and also the current disadvantages. So the literature review is divided into 5 parts about the AR holographic visualization, AR 3D holographic instruction for assembly and fabrication, AR immersive design, AR user interface for robotic operation, and AR assisted human-robot interactions. And after that, we publish an article called Review and Analysis of Augmented Reality AR Literature for Digital Fabrication Architecture in the Journal of Automation Construction, which is based on the information that we found in journal publication and also conference papers in the field of using AR technology in architecture, engineering, robotics, and digital fabrication area, published to date from 2010 to 2020, which describe the current state of art of AR and robotic technology in architecture field and their limitations. So after integrating the data, we actually found some research gaps in the design method and robotic operation area, which need the help of augmented reality to improve the current method. For example, like design method, the computer-aided architectural design and modeling software is still limited to a 2D-based screen, which lacks the intuitive meaning of on-site visualization and modification. As the design is done outside of the building site, so there might be disparities between the design and final fabrication. And also in the robotic operation area, it requires complex knowledge and skilled programming workers. So which is an expertise that traditionally we cannot find in architectural participants. And although there are many robotic operation plugins in Grasshopper, but they still require architect to visual programming, which is usually inefficient and occurs many errors. So based on the research gaps, we proposed this on-set AI immersive design to fabrication framework for the masonry structures. And the main research question is about what is the new AI-assisted design to fabrication framework for robotic assembly. And this is the flowchart of the basic AI-assisted design to fabrication framework. So we have several case studies along the framework to validate the proposed assumptions and to get the findings. And let me start with the design part. So first is the first phase of my research is AI immersive design. So in this part, we create two ways. The first is screen-based method, and the second is the gesture-based method. But before that, the user need to convert on-set environment into digital meshes by 3D scanning the in AI environment to set the immersive design base and the boundary plane. The boundary plane we set is for the robotic operation because the robots have some operation radius. So we have to make sure that our design is already in the operation radius. So first is the screen-based immersive design input method. It is suitable for the smartphone and tablets. So in this system, we preset different algorithms with suitable shapes. So the user need to choose an algorithm first and change the parameter or set or settings to design their own structure. For example, in this case, for these brick columns, we can change the height of the column, the rotation of the whole column, and each pattern of every layer, and also each brick, the rotation of each brick, and etc. So we use the AI-assisted user interface, where you could interact with the parameter settings on smart device screen and preview the design outcome on set as the 3D holograms. So the data will transform from your screen-based inputs to the design software through AI environment. And about the gesture-based immersive design method, it is suitable for the AR headset like Microsoft HoloLens. So in this system, we preset different algorithms with suitable shapes, and the user need to choose an algorithm first and use their hand gestures to interact with the different parameters. For example, in this case, we will let the user to set the curve on the ground first, so they can use the hand gesture by air tap to set the different control point. After that, there will be a smooth curve generated along the control point, and the user can play with that control point to make the shape perfect. After that, the surface will generate along the curve, and there will be several control points on the surface as well for user to play with. And after that, we can use the user interface from the HoloLens to set the breaks, like the gap of each break and the rotation of each break. So the data will transform from your hand gesture or even the voice command to the design software through AR. And it is a more intuitive method compared to the screen-based input because the user can fully use their two hands instead of one hand holding a device. So these are different outcomes of different algorithms in our part of the design database. So if the user want to do more specific shape, they can also create their own parametric design algorithms and export the related interactive parameters into the AR UI to interact with. So this AI immersive design process does fulfill our predetermined assumptions. So as a result, the immersive design phase is suitable for various interactive input modes and support different customized algorithm settings. So this onset design and preview function break the conventional 2D-based design method and provide designers with a 3D to 4D immersive perspective in AR for more practical design experience. And the second phase is the AR-assisted simulation. So after the immersive design, the structure will be sent to the simulation phase. So the physical performance will be shown as holographic animation on set before the structure is built. So the user can somehow get the feedback and preview first, figure out where is the fragile part that need to be modified more, or which part of the structure need extra adhesives. And after the physical simulation, the third phase is the AR-assisted fabrication. So in the fabrication part, we also create two ways. The first is manual fabrication, and the second is AR-assisted robotic fabrication. For example, like for the manual fabrication, we use the holographic instruction for manual assembly. So the AR-assisted assembly method has the potential to reduce the time normally when we spend the time translating the traditional 2D documents to a 3D real project. And it will improve the efficiency of the entire construction process. So the user just need to place the brick in the correct 3D holographic location, and the AR-assisted guidance no longer require any skilled construction workers, and it creates a new method that the designer and also the construction worker can be the one and the same person in the design to assembly system. And about the AR-assisted robotic fabrication, we create programming robots by hand gesture. For the two key points of operating a robot, the first is the trajectory, and the second is the command of an effector. For example, in this case, the trajectory is the movement of the robots, and the command for this case is for the end effector gripper to close and open to pick and release the brakes we need. So in our system, the user can use their smart device or even their hand gesture to set the trajectory planning point, trajectory control point to tell the robot where it needs to be moved. And for pick and place operation, we set the command open and close for the gripper. So the user can actually point out the pick location and also the release location in the AI environment to tell the robots where to pick and where to release. And in our system, we have an optical avoidance system. So after the structure is being built, we can use the arc marker to change the physical structure into the digital one to tell the robots. And the robot will generate a new trajectory to avoid the collisions. So this method gives architects and the designer possibilities to achieve the complex shape digital fabrication by themselves. And the AR-assisted robotic fabrication is a safer and more effective method to operate the robots through AR with onset gesture commands and also the holographic trajectory simulation. So all the computer science programming techniques has been pre-coding in Grasshopper. The user just need to use their hand gesture to operate. And they can operate the robotic fabrication layer by layer or brick by brick, depends on their assembly sequence. So in this way, the robotic workflow will not require specific knowledge of computer science or programming. And even unskilled architecture students, they can easily manipulate this process. But after using the foam brick for test, we start to use the real brick for the final assembly. So during the test, we found out several several problems, like we need the specific fixed location for feeding the bricks, which is not flexible. And we don't want to build or buy any complex brick feeding installations, which are difficult to use on set. So we create the target location recognition system by the Kinect sensor RGBD camera to scan, to recognize, and also analyze the brick location, which need to be picked in real time. So this method frees the automated brick laying from fixed brick feeding location and also the installations, and provide a more flexible on-set brick feeding method. And also we create an AR-assisted human-robot collaboration method for the adhesive applications. So the human worker can see the brick, which is in operation in white outline, and also the area that needs the adhesive application in red. So the user just need to follow the red holographic guidance, hold the mastic sealant gun, and apply the adhesive at the constant speed until the virtual red holographic area is filled by the adhesive. So this method can reduce the material waste and also avoid the messy use of robotic motor adhesive application on set. So the validation of our workflow is achieved with the design to assembly of two real scale building elements, a parametric masonry wall and also a column. And the final goal is to make the whole AR design to assembly workflow simplified and modified for the architecture scale elements and applications. And the last is about the thesis writing. So I will publish several journal and conference paper along my research from the literature review to research outcomes. So if you are interested, you can search about them. The first is the literature review I just talked before, and the second is ARDJ component, which described my research framework concept, and it is published in the SIGRADI 2020 Cadria 2021. And the third is the AR robot, which described the AR-assisted robotic operation method, and it is published in SIGRADI 2021. And the last is the augment bricks, which describe our physical framework tests and findings. So that's published in CDRF in Tongji University, China in 2022. And now we are preparing more about the camera target location recognition and also the AI immersive design papers. And the last thing that I would like to tell us is that I will hold a 3-day online workshop on SD platform this August. The topic will be AR-assisted robotic assembly in architecture. So you are all very welcome to join us if you are really interested in AR technology and robotic fabrication area. So you can find more information on the SD platform. So that's all for my presentation today, and thank you for listening.
Thank you so much. Thank you very much. We will have question sessions after SangHyun's presentation. So SangHyun, please share your screen.
Thank you. I'll start my presentation. Sorry. Can everyone see my screen? Yep. Hello, everyone. I'm SangHyun Suh, who is an architecture technologist and the designer. And thank you for inviting me for the a visiting school social algorithm 9.0 for the K something. And for those of you who doesn't know me, I would like to introduce myself briefly. I'm an architecture designer, an architecture technologist who's interested in the synthesization of an agency of human being and the machine through the computational design. My projects orbits around the finding new aesthetics from the AI-driven design utilizing machine vision as a tool, and the inspiration of the design. Today's lecture is going to be in mainly two topics, architecture as interface and then the interface as architecture. What I mean by that is that first for the architecture as an interface is with the advancement in the building technology and the smart home devices, we're not so far away from the true moment of IoE, Internet of Everything. It means that the role of architectural design that integrates such technology is a crucial. And the next, the interface as architecture is that in the contemporary design practice, designing your own workflow in the computational design is to designing an interface for design. And your design interface is your watermark for your authorship and the space for your generic design. Carefully selecting and creating the process is essential to the contemporary design practice. So with that, I would like to introduce this idea of the K concurrency, working with the theme of the this year's social algorithm 9.0. In computer science, concurrency is the ability of different parts or units in program algorithm or program to be executed out of order or in partial order. It means that it would act as if it's one thing, even though it has many parts, and then the overall, it's the calculating or going to execute something as a whole, even though individual parts are processing its own data or whatever task they're given to in parallel condition. For example, for the Seoul is a multicultural metropolis that houses many unique conditions within the neighborhoods. For instance, Gangnam and Ganggu looks very different, feels very different, and then different types of people live there. And what makes Seoul is not by one area, but by multiple unique and then mundane neighborhoods working together to make the image of Seoul. And these are the images of the Seoul, many different parts. As you can see, some parts are very traditional, some parts are very modern, contemporary, and then some are more dynamic, some are more more quiet and then more calm down. And there are multiple parts multiple styles of living conditions. For instance, apartment, very quintessential living style of Korea. And there are these millions of people using the Jjimjilbang every month, and there is a very unique typology that is very unique to Seoul in Korea. There is Goshimwon, which is this very tiny room that they can only house one person maximum. So the result of a concurrent computation, Seoul exists. The reason why I bring this up is that this tool called the TSNE is working in quite a similar manner. It's originally a statistical analysis tool to create visual representation for data sorting. So as you can see, here are textual information, there are image informations, but then you see the congregation of the various types of data from different categories, creating this the clouds of the things that's relating to each other. And then the location of these images are based on their similarity to their neighboring data in terms of the aesthetical qualities, in terms of the formal qualities, and so on. And then these are more examples. It has many different types of nature conditions, human bodies, and then the textual informations. Many different things, but then at the end it creates a certain pattern that allows certain data sets to come closer to others, and then that's this whole lot of image working together to create this image. So it's each image is contributing to the aesthetic or final result of the aesthetics of this result. And this is more examples. This is only images. You can see that the flowers are closer to the fireworks, and then you can see the segregation of the green fields, and then there are a lot of the background images with the nature, with the skies, and there are some castles, and you can see the patterns, how it creates like groups of objects within this field condition. And this is textual information. You have all these different types of the linguistic symbols, and then you can see these the conglomeration of the different parts of the object, creating a pattern to visualize what's similar to the others and what's different from the others. And then this is the image of there was one image of a cat, and then if you segment these into multiple images, you can see the pattern in this data set, that it is really a powerful tool to sort out each individual parts into smaller groups. So it's a great tool for segmentation of existing hierarchy within the object to reconstruct the relationship with the non-biased perspectives. For instance, if human is looking at this image, you would think that the eyes are to be on the center, and then there is a mouth here, there's ear here, and then there's a body here, and then there's a tail here. So that's very human-centric thinking that is based on the existing reality. But then what's good about this TSNE as a tool, image creation tool, is that it can suggest multiple alternatives to what's already existing. This is the image of a certain park in Mexico, and then you're creating this, you're dissecting and then recreating the image of a park through this assemblage, to suggest the alternative layout. And this is some biological form that you find in the nature, and you can also segment these into create some sort of a hybrid condition that is not meant to be in the nature, but then find its interesting aesthetical qualities through these sort of experiments. And this is one of the typologies that you can easily find in Korea. It's the patterns that you find in temple for the wooden construction, and you see some conglomeration of the patterns, and then based on the depth and based on the different color types, to create this weird typology, but then weird alternative the image. For instance, here, like there is this the joist for the roof going through as a cross-sectional condition, but then these are purely textural information. For a structural reason, this wouldn't make sense, but then one can make an alternative version of the this sort of like a temple layout to create new image and the new design through using this process. So and this is the two different facade condition. One is made with the travertine, one is made with the glass facade, and you see this. You see the reassembly of the existing facade condition to create this interesting patterns. This one image on the right corner is the travertine architecture that has some shading devices, that has some turning points. Now it's creating very like chaotic, but then somewhat relating to each other. One image relating to each other. So it creates alternative aesthetics to the existing building in quite simple manner, using this tool PSNE. And through this kind of a research, I wanted to design my own the workflow or the interface for the design. And then since I live in Los Angeles, closer to the Los Angeles downtown, I made the Los Angeles downtown as a subject, and then the objective for me was that the dissect and then reassemble the downtown at Los Angeles with no hierarchy based on the preconditioned historical or cultural significance. For instance, when you think about the LA architecture, like most of the people will instantly think about the Disney Concert Hall by Frank Gehry, and then the Broad Museum by Diller Video, and maybe Staples Center that is quite popular for the events. So these are the canonical examples that is based on the historical and the cultural value. But I wanted to evaluate these the facade condition in the LA purely based on the aesthetical qualities. So there are two parts in downtown Los Angeles. One is much older, and then one is the newer condition. Just like the Samcheongdong in Seoul, there are like new parts and then old parts, and then they're mixing, and then those kind of a new and old condition creates a certain rhythm that's very unique to the Samcheongdong. And this one is, as you can see, mostly older parts, but then there are some anomalies like this because in the older part of the downtown LA, there is a fashion district, and then this is the storefront of a Paul Smith. They were in the renovation period, so now I have this color, and then there are some flags for the advertisements that was in different colors. But then overall, it has a granite the facades or any or different or variations of the stone facade that had the quite opaque condition compared to, let's say, the new architecture. That is mostly the glass facade, curtain wall construction that has much more transparency and translucency into their the design. And this is the result of how they come together. You can see that most of the older stuff here is segregated on top of the image condition. These are brick facade. These are this is also brick facade, but then there are a mix of different types of the stone construction, stone veneer conditions for the facade over here, and then the rest of it here is mostly glass facade and then the contemporary types of the construction. And this is another experiment that I did. It didn't include it. I did not include this in the my final result, but then it was also quite interesting experiment to mix the industrial and the suburban area of Los Angeles and how they mix together and then create a certain pattern. When it comes to this type of less, let's say, identifiable pieces compared to these downtown area, it had a little bit hard time to recognize what's what belongs where, how can they categorize it based on the aesthetical qualities. Surprisingly, the suburban the houses were not so different from the industrial area to the eyes of a machine in this experiment. But for the visualization, this is the images that I collected myself throughout the downtown LA, and I processed it through multiple methods, and at the end, it created the this sort of assemblies. One thing about the TSNE is that based on what kind of variables that you put in, the amount of the aggregation varies, and it creates a different representation every time you run it. So it could be used as your interface for the composition harvester. Once you have all these data sets, you can have millions of different facade conditions based on the context information that you have in your data set. And as I just said, TSNE could be used for the compositional tools, varying perplexity, which is the variable in the TSNE, for different mixing aggregation results based on each element's affinities towards the other in terms of a feature, like color, geometry, aesthetics. one is more similar to another, whereas the one, like for instance, a Greek facade was very different from the, let's say, the glass curtain walls. And to make these 2D images into a 3D facade conditions, I harvested and then I harvested compositions and then put these into like 6 different conditions, and then trying to see what kind of a different 3D geometry arise from this sort of different filter conditions. So here, this is the closer to the what it is in real life, and but then this is the when I apply the a certain threshold to the image to create more exaggerated or minimize the depth conditions to create this hybrid condition over two different let's say sensors for the aesthetic purposes. And this one is doing the same thing based on this geometry. Because this was a glass wall, when you apply this displacement to it, most of the glass will go away, and then the most of the opaque part will arise as a more more prominent the condition, and then you can create this glass facade that is closer to the reality, and then the one that is filtered by the threshold and this displacement to be this hybrid condition of a geometry. These are the simple point clouds that I generated from the depth analysis of the images of these the facades, and then I am using Houdini to create this 3D the tessellated surfaces. For instance, you can tessellate the surface based on the displacement, and then creating different the reading of these the geometry into many different interpretation of this image into the 3D model, and then one could create this the complex tectonic so one can make the 3D model that suggests the very complex tectonic conditions for each facade. And this is the kind of the process. So from the image that you just saw, with the height difference, you can create this sort of various conditions, and then you can overlay. I could overlay all these informations to create something that is outwardly, but then suggest some alternative the reality to the what's already existing in the downtown LA. Sorry about that. And for the visualization, you see that this was originally tiled surface with the granite, but then you can iterate this with the various tile sizes, and then the various the opening sizes to create this very highly articulated geometry. And this was the final result for this project, where this facing to the west, which was the newer part of the town, and then this facing to the east, which was the older part of the town, has is assimilating to the existing surrounding. But then when you look closely, it actually creates a little bit of a diversion from the existing context to suggest the alternative aesthetic qualities from the one that we already have in the downtown. I'll skip this. And this is another aspect of my research focus, which is um, architecture as interface rather than the interface as architecture. This is trying to integrate as much as information as possible in the wall assembly of the speculative architecture. All these different panels in different orientation has a unique assignment as a numerical number, and then these numerical information represents all these different types of addresses, just like the HTML addresses on the internet. And on top of that, there is the visual information to overlay on top of the geometrical condition to create these weird textural the things, but not just for the texture's sake. There is a reason for it. One was more so right here in the more of a neutral tiled condition, the machine vision can sense the human being at the much more like a higher fidelity, and on the texture that I generated here with the many people's the texture that I generated with the machine learning tool, this has a lot of the faces and then human body parts as the textures in the wall, and then this creates a diversion to the background, so that the object detection, the mechanism in the AI doesn't act not so great, doesn't perform not so great, so that when you're in front of this type of a wall, you can avoid the object detection to ensure more privacy in your future speculative home. This wasn't just randomly generated. I ran the object detection on the street of the downtown LA, and then I got this exact moment where this person was detected at the 100% accuracy, and then I used the textual information around her to create this the texture information using the style transfer method on the existing wall. And then it creates this variations of the texture information. And here, this is the one that's called the bad wall. And then this bad wall has so many people in it, and the data set has so many people in it. So it creates this weird texture that looks like it has so many people inside of this wall. And yeah, there are more stuff. For instance, like I can have a reflective paint applied to make it as like a pivot point of this individual tiles, to create another layer of information to visually represent like the address of this particular wall within your the room. So for instance, like this is a reflective condition that can be easily detected by the machine.